All right, so what what this is cigarette smoke rising, and let's see what is going on here. Okay, so here's a lit cigarette, and what that does is it's hot, and so what it does is it warms the air well as the and smoke gets caught in it. And when you warm a packet of air, what happens? What happens if you warm air? It expands. Its density gets less than the density of the surrounding air. When its density is less than the surrounding fluid, the density of this object is less than the surrounding fluid. So if you put an ice cube here, the buoyant force will be greater than the weight of the fluid object, and there'll be a net force acting on it upward. So this packet of air feels a net upward force. Okay, because the buoyant force is greater than the weight of the packet of air. Okay, so that's true as long as your density is less than the surrounding fluid density. Okay, so you'll accelerate upwards. So you're accelerating upward. When you're accelerating, your speed is increasing. So you see the speed of this air packet is increasing. It's continuously increasing, and you see what is happening is this is laminar flow. Okay, the flow is laminar below a critical speed, and above a certain speed, then it becomes turbulent. Okay, turbulence is bad news in many situations. Okay, so if you have turbulence over your wing, then you lose lift. Okay, if there's turbulence in your blood vessels, then to maintain flow rate, your heart is having to work much harder. Okay. All right, so above a critical speed, turbulence sets in. Okay. So he was a very smart physicist, and here's a quote by him. So he was a contemporary of Einstein. He was one of the founders of quantum mechanics. Okay. He says when he meets God, he'll ask him two things, relativity and turbulence. And he thinks that even God doesn't understand turbulence. So nobody understands turbulence. Okay. So fluid in motion transitions from steady laminar flow to turbulent flow above a critical speed, and that's characterized by a Reynolds number. Okay, a dimensionless number tells you what the Reynolds number is. So if you're above Reynolds number, you're in turbulence. Okay. So fluid motion is very complicated. So everything we'll talk about applies here. It doesn't apply here. Okay. So this is laminar flow. Everything we'll talk about is for laminar flow, and also we'll talk about frictionless flow. There's friction in liquids is called viscosity. So we'll talk about flow where there's not much viscosity. Okay. So for instance, we won't be able to apply anything to honey. Honey has large viscosity. Okay. So we'll get away with applying it to water. Okay. So this is laminar flow. We'll talk about steady flows. So if it's a river, the flow is steady, meaning the velocity of the river is not changing with time. Okay? This is turbulent flow. Okay? So for instance, if you have turbulent flow, what this is so if you have viscosity, you have to maintain pressure difference. You have to maintain a higher pressure here and lower pressure here to make the fluid flow. So for instance, that's why your heart has to pump. Okay, if your blood was frictionless, your heart would not have to pump. Okay, you'd get free flow for all your life. But unfortunately, there's friction, and so your heart has to pump. Okay, so what this is showing you is this is a flow rate, and this is the pressure difference between the ends of a pipe. Okay, so if the flow was laminar, for this pressure difference, you would get a higher flow rate. If the flow becomes turbulent, for the same pressure difference, you're getting a lower pressure flow rate. Okay, and you see it gets worse the greater the turbulence. You're only getting this much flow rate, okay? And that would be the flow rate you wanted, laminar flow, okay? So for instance, if you have, for Usain Bolt, his blood vessels are like that, okay? And he can maintain a higher flow rate, and let's say my arteries are blocked, I can only maintain that flow rate for that given pressure difference, so I'll be huffing and puffing. So turbulence decreases flow rate at a given perfusion pressure. So here's laminar flow. All right, viscosity is friction in a fluid. Okay, so and what does friction do? Friction converts kinetic energy to heat. Okay, it converts it to heat. Friction can. Okay, so viscosity causes part of the kinetic energy of a fluid to be converted to heat, internal energies. Okay, heat energy. Viscous forces cause resistance when two adjacent layers of the fluid move relative to each other. Okay, so it turns out, so here's generally the velocity profile of a fluid moving in a pipe. Okay, so the fluid is moving, the central cylinder is moving the fastest, and the fluid at the end is almost at rest. And that's how plaque gets deposited, because this blood is flowing very slowly, so all stuff can collect on your artery walls. Okay. All right, so we are going to consider ideal fluid. So here are the characteristics of an ideal fluid. It's frictionless, it's incompressible, and so on. It's non-viscous, frictionless. Flow is steady, meaning the velocity is not changing. So if the speed is that right now, you can come back 10 minutes later and the speed of the liquid is the same at that point. Okay? Flow is steady, it's incompressible, and so on. But we'll still apply what we learned to gases. So as long as gases are not moving too fast, as long as they're moving much slower than the speed of sound in that fluid, this stuff will apply. Okay. Is irrotational. The fluid has no eddies in it. Okay. Irrotational means if you put a little paddle wheel in there, if the paddle wheel is rotating, then it's rotational fluid. It's a simpler way to say is there's no eddies. Okay. So everything we'll say will not apply when there are eddies in the fluid. Okay. Okay, so the first equation we'll talk about is the equation of continuity. Okay, and this is stating a simple fact. So let's say you have a pipe whose cross-section area is changing. Okay. Well, let's say 2 gallons are flowing in per second here. How many gallons of fluid has to flow out per second? 2 gallons, if there's no leaks in the pipe. So it doesn't matter what the cross-section is, what is going in has got to come out. You know? And the flow rate is given by the area of cross-section times the speed at that point. So if the area of cross-section increases, the speed has to decrease. Okay? And that's the equation of continuity. All it's saying is what is flowing in, the rate of flow is the same everywhere. Okay? So if 2 gallons a second are passing at this point per second, 2 gallons a second are passing at that point. Okay? This is the equation of continuity. So if the area of cross-section increases, the fluid slows down. Okay? And this is important. So here's one application. Okay? So when blood comes out of your heart in the large aorta, it's flowing at about 30 centimeters per second. It's Blood is flowing at 1 foot a second. What's the job of the blood? Yeah, so it's to carry oxygen and nutrients to the cell. Okay, so there's this good stuff that needs to be delivered to the cells. Okay, so now when you get to the cell, that good stuff is being exchanged via diffusion. Okay, diffusion is higher concentration stuff will diffuse into the cell, into a lower concentration region. Okay? But that's a very slow process, and you can only transport that tiny distances. Okay? So this is going at 30 centimeters a second. So if blood passes by the cell at that speed, there's no diffusion going to happen. Your cell is not going to get oxygen. So what do you have to do? You got to slow down the blood. How do you slow down the blood? So you just learned the magic formula. You have to slow down the blood. You have to increase the area. Okay. So this blood vessel branches into tiny capillaries. Okay, so this blood flows into these tiny capillaries, and the area increases. So this blood slows down to about 0.03 centimeters per second. Slows down by a factor of 1,000. Okay, and so it slows down to about 0.3 millimeters a second. Okay, so the area increases by that factor. And now when the blood is going slow, there's enough time to exchange stuff. Okay. So that's what the body does. That's why you have so many capillaries. Okay. All right, so this is the equation of continuity. All right, so you saw that if you have a pipe of different cross section, what is flowing in has to flow out. Okay, so the cross section determines the speed. Okay, now so okay, so V2, V1. So V2 is less than V1, right? The speed is decreased because of that. Now let's do the following. Let's make the following change. So we'll have the same cross section, except that now we'll also raise the pipe. Okay. Well, the cross section, this cross section is equal to this cross section. So this speed is equal to that speed. But what happens to this keychain when it rises up? It slows down. So why the heck did this guy not slow down? So what happens is the pressure here, you have to push harder here. The pressure here is greater than the pressure here. Okay? So Mr. Bernoulli figured out the relationship between all of that. Did you guys understand that? Yeah. And here is Bernoulli's equation. Okay? So in a fluid that is flowing in laminar fashion, you can go to any point in the fluid. This combination, pressure times, this is the kinetic energy per unit volume. This is the potential energy per unit volume for the fluid. The sum of these three terms is constant. Okay, so you go anywhere in the fluid. But here's the most important thing I want you to remember for the rest of your lives. Okay, so let's say if you have a flat tube, okay, if this doesn't change, so we'll cancel this. The faster a fluid is flowing, the smaller the pressure. Okay, so greater the speed of a fluid, the lower the pressure. Okay, so that's the important conclusion. So, and let me show you an app. Okay, so again in this fluid, okay, so we'll measure the pressure. The pressure here is 120 units, kilopascals, and 120 kilopascals. Okay, so if the fluid is frictionless, then the pressure is the same. You don't have to spend any money to get the fluid going, or okay, to keep it moving. But if there's friction, then the pressure here will have to be higher. Okay. All right. Now, what we'll do is also we'll measure the speed here. So the speed is that, and the speed everywhere is the same. Okay. Now we'll make the pipe narrow, and you see the speed increased. Okay. Because area of cross section times the speed is constant. Okay. All right. Now, okay. So you see, okay, what I'll do is I'll illustrate. So this is a non-viscous fluid. Remember, the pressure was the same, and I'm not going to change the cross section. I'm just going to lift this up, and since the speed there was the same, the speed is the same, it didn't slow down. The pressure here has to be higher than the pressure there. Okay, the pressure there is 120 units. The pressure here is 130 kilopascals. Okay, so the pressure had to increase to maintain that speed. Okay. Anyway, this Bernoulli's equation captures everything. The sum of those three terms is constant. Okay, so the flow has to be non-turbulent and irrotational. So it's for laminar flow only, for Bernoulli's equation to be valid. For an ideal fluid flow, it's frictionless. Using conservation of energy principle, Bernoulli showed that. Okay? All right, so now we'll, so pressure plus kinetic energy per unit volume plus potential energy per unit volume, the sum of those three terms have to be constant. Okay. Now we'll consider situations where y is not changing, so that is constant. Okay. So if you have a streamline everywhere, so streamline is here's, okay, so let me okay, so here's a streamline. Okay. I wanted to see a streamline around a car, but anyway, so here's a streamline, and you can calculate the sum of those three terms at any location on the streamline, and that'll turn out to be constant, and that's what Mr. Bernoulli says. Okay, so 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 that's become turbulent flow, but as long as the flow is laminar, you can calculate the sum of those terms around any point at any location, and the sum of those terms will be constant. Okay. All right. So here was air, a packet of air that's going at a certain speed, and now when this air has to go in a narrower region, see, its speed has to increase. If its speed increases, the pressure decreases. So the pressure of this air has decreased. This pressure where the air was flowing slower is higher. So when you drive next to a semi, you will feel an attractive force of the semi. Oh, as a motorbike cyclist, you feel a lot more.
Oh, yeah, especially for you.
Yeah. So, all right. So again, the faster a fluid is flowing, the smaller the pressure. Okay? So that's how airplane lift works. So this airfoil is designed to make the air flow faster over here than here. Okay? And the lift, so the pressure there is lower and pressure here is higher. And the force of lift is pressure, high pressure minus. Okay. So the plane is flying this way. Okay, now this pressure difference between the top and the bottom depends on the speed at which you're flying the plane. When you fly the plane slower, this pressure difference becomes smaller. So the plane is not falling out of the sky. How do you prevent it from falling out of the sky? This has become lower. The lift, you need for the lift to be equal to the weight. So what do? This becomes smaller, then you have to increase this. So that's when you put out your flaps. Okay, so when you come in for landing, that's what happens. You're slowing down, this is becoming smaller, and so you're increasing the area of your wings. Okay. Pressure difference, because there's a speed difference, accounts for the lift. Okay. So here's laminar flow, and if the angle of attack becomes too large and you have turbulence set in, now the pressure here is not lower than the pressure here. In fact, the pressure can be higher here, and so you lose all lift. Okay. And also in turbulence, the pressure is random. So turbulent flow is characterized by chaotic changes in pressure and flow velocity. And also you have drag forces. Okay. So the increased drag and the increase in pressure you lose your lift. Okay, so in tennis, if you play tennis, a lot of tennis players put topspin on the ball. Why do they put topspin on the ball? Yeah, so the reason you put the ball is traveling in this direction. Okay, so you've hit the ball in this direction, and that's the relative velocity of the air. Okay, so if you put a topspin on it, and that's what the fuzz on the ball is about. Okay, the fuzz on the ball catches the air much more. Okay, so when the ball is spinning like this, it's the air, more air is flowing like that. This air is flowing faster, so the pressure here is lower. This air is moving slower, this pressure is higher, and it'll create a large enough downward force. So you hit the ball with the top spin in that direction, there's a force, and it makes the ball fall inside the line. The harder you hit, the more top spin you give, the greater this force, the more likely it is to fall inside the baseline. Okay. So if you hit without its spin, it will more than likely go outside the baseline. Okay, so you have to be very accurate to put it inside the baseline. So this gives you more room for error. Okay, the more top spin you give, you can hit it harder, and you can be still assured that it'll fall within the baseline. Okay. You guys might have seen, so this is the Magnus effect, and here's a very cool video showing this. Where's the Magnus effect? Okay. Have you guys seen this video? Yep. All right, so this is for the benefit of those who haven't seen it. Okay, what's going on? Is it downloading? I mean, shouldn't it be streaming? All right, go watch it, and it's posted on the core shell. Should I reload it?
I'm like so starstruck.
I know. He's so much taller in person.
I'm struggling with his proportions.
Yeah, because you're taking too long.
Okay.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens. All right, you guys good down the bottom?
Thank you. We're watching.
Ready? Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it's falling, so that was really cool. Alright, ready? Whoa, look at that go! It's incredible.
So pretty amazing. So when you put a spin like that, the air is going faster
This is very
along here.
I literally just dropped it
no, the air,
with a bit of spin,
it's
like I
catching
didn't
there
even
and
throw
it's
it, and
going
it just
faster
took
along
off.
here.
Like, we
The
had
pressure
no
is
idea that was
lower
going to
on
do
the
that.
front. and
But
it
yes,
gets
in the water, please. So that was a pretty amazing experiment with some really interesting results. So the first one.
All right, so here's a device that you use all the time. Again, what does Mr. Bernoulli say? When fluid is moving faster, the pressure at that location is lower. Okay, so you can do this. So here's the liquid, and you stick a tube here. Okay, and now you blow air across this tube. Okay, so if you blow air across this tube, this air is moving fast, the pressure here will decrease. And this atmospheric pressure will push this fluid in here, raise this fluid, and the height will depend on the pressure difference between this point and the atmospheric pressure. So atmospheric pressure will push the fluid in here, and that'll get caught and get sprayed. So that's how perfume bottles work, that's how those spray bottles work and all that. Okay, so all you're doing is blowing air. Yeah. Viscosity. What is viscosity? Viscosity is friction in a fluid, and it's denoted by eta. Okay. And here's how you measure it. So, for instance, if you wanted to measure viscosity in honey, what you can do is you can put a slab of wood there, and there's the wood. And what you do is you find out what force you have to apply to this slab to maintain constant velocity. Okay. If there was no viscosity, then you could get it in motion, and then it would remain in that motion. It would maintain its speed. But if there's viscosity, you have to maintain a force. You have to keep applying a force to maintain a constant velocity. Okay? And so that force is related to the viscosity of the fluid. A is the area of the plate, V is the speed at which it's moving, and L is the distance between these two plates. Okay? All right, so if you have a viscous fluid and you want to pump this fluid through this pipe, you have to maintain a pressure difference. Okay. So, for instance, if and this pressure difference is related to how much work you're doing. Okay. So this is your electric bill. So the flow rate, the gallons per minute or whatever, the flow rate is equal to the pressure difference times the radius to the power 4 divided by 8 times the viscosity divided by the length of the tube. And here's another thing. Okay, so if you get plaque in your arteries, if the radius decreases by 10%, okay, so 0.9 times to the power 4, do 0.9 times to the power 4, 0.9 to the power 4 is 65%. The radius decreases by 10%. The flow rate decreases by 35%. Okay. So you see, to maintain the same flow rate, your blood pressure has to increase by 35%. Okay. Here's another application. So this is the pressure difference. Okay. So this is the viscosity term. So when they pump oil from in Alaska, you have to maintain a pressure difference to pump the oil. Do you guys know on the pipe they have heaters on the pipe in Alaska? Why do they have heaters? I'm sorry? So with the heaters, what you're doing is you're decreasing the viscosity. Hot oil, the viscosity is smaller. And so now you have to maintain, if the viscosity is less, for the same given flow rate, now you have to maintain a smaller pressure difference. And so it costs you less to heat than to increase the flow rate. Okay, so heating the oil and then pumping costs you less than just pumping cold oil. Okay?